Hello to all my wonderful students out there. You got Dr. Mandis here. Today we're going to talk about acids and bases, and in this case, we're going to talk about the strength of acids and bases. Before I do that, I just want to say, look, how fluent you are in all of this chemistry is really helps you to learn it. When I just said acids and bases, what did you think? Because I got to tell you, if I said glove, couch, sofa, refrigerator, things like that, images are popping into your head. How fluent are you? When I said acid, do you remember that acids have to donate H positive, form hydronium in solution? Did that just pop in with you or not? It needs to pop in with you. And if you get that, then you can understand more. But if you don't get that, then you're constantly reaching and scratching your head and trying to put two and two together. So as you proceed through, or proceed, however you want to say it, as you move through this course, man, you really got to think about, hey, how much these definitions and terms do I really know? Because it'll help me to relate things together. But anyway, we're talking about acids and bases. Acids are compounds that donate H positive. Cool. All right. So to do that, they need to break that bond. So if you look at this groovy little equation right there, okay, there's a bond between the H and the Cl. That bond's got to get broken. Alrighty, that's gotta get broken. And much like when you were little and you broke something, you said to your mom and dad, "Oh, it's like that when I got here." Things just don't break on their by themselves. Something has to break it. In this case, for the most part, it's water taking that H from the acid. The acid doesn't give it up so much as the water takes it from the acid. So here you got, I showed you like the O is grabbing that H, breaking the bond, leaving the electrons behind in the Cl. All right, forming our products. There's your hydronium that the acid forms. The more that hydronium that can get formed, then the stronger the acid, the less weaker the acid. What it all boils down to is not how much hydronium gets formed, but really how easy is it to break that bond. Our H taker is water, so that aspect isn't changing. The aspect that changes is the bond strength. The weaker the bond, the stronger the acid. They go opposites because if the bond's weaker, then more hydronium is going to get formed. If the bond's stronger, less hydronium is going to get formed. The weaker the bond, it's easier to pluck it off, and so it keeps on snagging it. The really strong acids, I always like it. The bond is kind of like bad Velcro. If it's a strong acid, man, you can push Velcro together as much as you want, but if it's really all got all sorts of hair and fibers and crap in it, the Velcro never stays together. Fresh Velcro, man, that stuff's like that's best glue ever. You can't take it apart. Well, that's kind of like the bond. Is it really, really kick-ass Velcro and really stuck on there? Well, that's a weak acid. If it's barely hanging on, such a strong breeze will blow it off, that's a strong acid. All right. The electron pair is your Velcro. That's your glue. Okay. Here's something you don't think about. I said, more glue. Stronger bond, less glue, weaker bond. Can you have more of an electron pair? Yes and no. Electrons are particles, but they're also waves. Alrighty, and so it helps to think of them as waves and think of them as being able to meander back and forth like a wave. Okay? What you can have is an electronegative substance in there sucking the glue out, pulling the electron density out of the bond. And I think I got something down here. There you go. I have four acids all hinging around the Cl. If you notice, we got our H stuck on, H stuck on, H stuck on, H stuck on. So there are your H's. But it's the back end of the molecule that matters. Here you have an O and Cl, and that is constant throughout all of them. Okay, so you have so much O and Cl. Chlorine's highly electronegative. You need to recall your electronegativity bit, that up in the top left-hand corner, NOFClBr. They're your most electronegative guys. F is number one in the rankings. O is number two. Then Cl, right behind Cl is N, then Br. So anyway, you got these highly electronegative guys on that OCl pulling electron density out. All right. So in here you have one O extra pulling electron density, but here you have two. So that's going to pull even more electron density out of this wonderful little bond right here. It's this electron density that's getting yanked in the other direction. Alrighty, and it's true. Okay, and when you get all the way down here, you have to HClO4. You have all those oxygens there, and those oxygens really serve as to pull almost all the electron density out of that bond, and that H falls off all the time. HClO4 is one of the world's strongest acids, and it's always 100% dissociated. Since we're talking about the formation of hydronium, if you recall, if we go all the way back up here to the very beginning, we had water, okay, reacting with your acid and it was making hydronium. We focused on how it was making the hydronium. I want to switch to how much hydronium is made. The weaker the bond, the more hydronium is made. Well, if you go back to your dissociation equation down here, the weaker the bond here, the more of this is going to get made. Well, the more hydronium concentration isn't, if you look at the equilibrium expression, this number here is going to get bigger. So if that number gets bigger, the Ka value gets bigger. So the stronger acid, the greater the hydronium, greater the Ka value. So you can either look at the structures or the Ka values. All right, depends really what you're given in the problem. Alrighty. So here we have our same structures again. Now I tucked in the Ka values. Alrighty. The Kas are right there. HCl is a really little Ka, 3.5 times 10 negative 8. When you go all the way down to HClO4, it's way too large to get measured. Okay, the HClO3, some guys call it a strong acid, some guys don't. The Ka is bigger than 1. So that's a lot bigger than 10 to the negative 8. So you see as we get more electronegativity through those extra O's, okay, you get more electron density sucked out of the bond and the acid gets stronger. In the last 2 seconds, the same thing holds true for bases. Bases react with water to form hydroxide. The more hydroxide that gets formed, then the stronger the Kb value. So the same gig there. All right, so you can go by the Kb or the Ka. Stronger value, stronger acid or base. I have a quickie little example problem right here for you. Which is a stronger acid? You can either answer it both ways, you know what I'm saying? You got HOCl, HNO2, HOBr. You have their Ka values. So cool, rank their Kas. There you go, man, okay? In those Ka values, the 10 to the negative 4 is definitely bigger than the other two. So HNO2 would be the stronger acid. It's going to generate more hydronium. If you look at it structurally, which I kind of did down here in the bottom, okay, you have an H attached to an O, H attached to an O, H attached to an O. So that's kind of consistent through all of them. If you look at the back end of those molecules, you have NO, N is number 4 in the rankings, right behind Cl, plus O, number 2 in the rankings. You have a Cl, and you have a Br. So NO has a lot more electronegativity, a lot more ability to withdraw electrons than Cl, and it's the stronger acid. Cl is more electronegativity than Br, and it is the stronger acid. So either way you slice it, through the Kas or through the structure, you can easily predict which one is the stronger acid. Hope this made a lot of sense to you. Practice it, learn it, like it. It's a good time. I'll talk to you later.